Hello, Stats class. This is lesson 8.2a, which is where we start getting really specific about confidence intervals for a proportion. Specifically, 8.3 is going to be about means. And so we're going to get a lot more details today. These notes can come after the quiz or before. It doesn't matter to me. But remember, we also have a quiz today on lesson 8.1. So I want to remind you of how we calculate that z-star thing first, because somebody asked me about that. So z-star is also called the critical value. And I talked about this in Tuesday's lesson, but I'm just going to review it with you real quick. So it is the z-score that cuts off or is the boundary for the middle, whatever percent you're working with. And most of the time we'll be doing 95%, especially at the beginning, and then later on we'll talk about what if it's not 90%, or 95, I mean. So for example, the middle 95% means I want in my normal curve to have 95% in the middle and 5% on the outside, which is split into 2.5% on this side and 2.5% on that side. Z-star is this value right here, the positive z-score that cuts that off. Technically, this one would also work, but it's the negative equivalent of that. But then to find that z-star, I need to think about this region right here, which is 97.5%. I got that by doing 95% plus half the extra. And so in order to calculate the middle 95% or the critical value for that, I would do inverse norm on the calculator 0.975, and just as so that it's written down, this is the 95% plus half the extra. I could make a formula for that, but I found that it actually confuses people more if I write down a formula for this half the extra thing. It's better if you just know that it's half the extra. So you would do that and you would get 1.96. And then if you did it with a different number in the middle, like 90%, you'd get a different z-star and a different number of standard deviations to go for your margin of error. So that's kind of a backtrack to lesson 8.1 because I wanted to answer that question for somebody. But let's move on. What we are talking about in this lesson 8.2 is we're talking about knowing p hat, which is our statistic. And we are going to use it to estimate the value of P, which is the population parameter. Or another way of looking at it is this is the sample proportion. And this is the population proportion. And I gave you the basics or the introduction to that in 8.1, but today we're going to make it much more formal. We're going to start doing the 4-step process for this, and I will walk you through those steps. So we're going to actually do the 4-step process twice today. It's going to be a little bit longer notes. I thought about trying to put them side by side, but I think it'll be easier if I just do the basics first and then an example instead of side by side. So the 4-step process is coming back again. We've seen it many times before, and that's kind of comforting. But here's what the 4-step process looks like with a confidence interval. We start with state. And specifically with the confidence interval, we need to state what it is we're trying to estimate, the parameter we want to estimate. Or the context. And then we need to say what our confidence level is. Just a quick example of this, but I'm not going to write it down. Say we have a bag full of red and white beans, and we want to estimate the proportion of beans that are red. That's our parameter. And then our confidence level is the second thing we should state. Confidence level is usually 95%. Okay, so here we go. Step 2 is the plan. Now the plan is to use that formula that we learned, but really the plan is supposed to be about checking conditions. Are we sure that we have our three things that are going to work? So we're going to learn to check these conditions as part of our plan, and we're going to get really, really good at that in all of second semester. It's going to keep coming back until it's just second nature. So I'm going to remind you of what we said in 8.1b of we've got our center that needs to be right, and that means we need a random sample, which gives us an unbiased estimator. We're going to check to see if that's true. Now, I can't do that right now without an actual example, so we will come back to that when we do an example later and talk about how to check. But right now, we're just going to think about that. The first thing we would need to check is it random? Second thing we need to check is the shape. I generally put them in this order, partly because this is like in order of importance, and partly because it's the same order that's in the formula, what we were talking about before, and we'll see that in just a minute. So the shape is we want it to be normal. We don't need the population to be normal. We can't control that. We can't control the sample, but what we're talking about here is the sampling distribution of all the p-hats. The sampling distribution has to be normal in order for this calculation that we did with z-star to actually work. And that happens, since we're talking about proportions now, we're going to focus in on the if NP and NQ are both greater than or equal to 10. And remember NP, actually, you know what? We don't know what P is. That's annoying. Since we don't know what P is, we're going to do P hat, and I probably should have put that in the last set of notes. And Q hat, both has to be bigger than 10. And that's basically the number of successes in our sample and the number of failures in our sample. We have to have our sample big enough to have at least 10 successes and 10 failures to make the calculations be accurate. Okay, that's something we can control if we're actually gathering the sample ourselves. The third thing is spread. And it is based on the idea of independence. And that is true if n, or sample size, is less than or equal to 10% of the population. So we're going to check that too. A lot of times this one will be a common sense thing. It's like, yeah, I'm pretty sure there's that many people in the United States. We don't have to know the exact population size to be sure that we have less than 10% of them. So we'll do that on an example in a minute, but I wanted you to have that written in your notes of this. Those are the three things you need to check. Step 3 is do the calculations. And we talked about the calculations already, but let's put it down again. It is our statistic, which is also called our estimate. Plus or minus our critical value times our standard error. In case you forgot, the reason it's called standard error is we're estimating it from a sample instead of getting it from the population. And we talked about this formula in 8.1b, but here it is again. The statistic in this unit, or in lesson 8.2 specifically, is p hat, and it is plus or minus z star, and times the standard error, which is square root of p hat q hat over n. So we're going to take what we know about our sample, which is p hat, and plug it in here and find q hat. And yeah, we'll know all of these numbers, and we have to calculate the z star. Z star, as we said above, depends on our confidence level, which is also called C. And it's that inverse norm. I'm not going to write it again, but we wrote it up here. In fact, maybe I'll put a big arrow. It's the C value plus half the extra plugged into inverse norm. All right, we'll come back to that when we do it actually with numbers. So then conclude is the part that I probably should have spent more time on before, but that's okay, I'm going to do it now. Conclude is your interpretation I should have left myself more room. It's the interpretation of what you just did. So here's how you write a good interpretation. You would say we are however percent confident, usually 95, that, so let's think about this for a minute. We found our estimate, we found our, I'm going to write this little guy again. We found our estimate, we went this far above, this far below. We are pretty sure that somewhere in that interval is the real proportion. That's what we need to write about. So we are 95% confident, or however confident we are, that the interval we just calculated, and we're going to use the numbers from what number to what number, contains the true proportion. I have to write this carefully because everybody always asks me what word that is. True proportion of whatever it is that our context would be. So if we're counting red beans, we would do the true proportion of red beans in the population. Okay. So that's how you interpret it. And we're going to do all 4 of those steps one more time today with an actual example. So here's an example of doing the 4 steps with a specific situation. Let's, instead of doing beans, because we've done that already, let's do pennies. Let's say we take a random sample from my huge penny jar, and let's make it a pretty big random sample. Let's go 102 pennies. And we find in our random sample that 57 of them are over 10 years old. Believe it or not, that is enough information. That's all we need to do a confidence interval. So there we go. We know how many pennies there are. We know how many of them were successes, and we can figure out how many failures. I'm just going to do the 4 steps. And I'm going to start by saying what we want to state in our state step is we want to state the parameter. We want to estimate, what is it we want to estimate? We want to estimate the true proportion of pennies in our population that are over 10 years old. And we need to say what confidence we want. I think just to make it different, because it would be good for your brain to see a little bit of branching out, let's do a different level of confidence than last time. Let's not do 95%. Let's say we want to be 99% confident that we are right. So things to mention in your state step. You want to mention the word proportion for sure. That's important because later we'll be doing means. This is our population. This is our definition of success. And this is our confidence level. So you need all of that information. When I say use context, that means tell who or what and what about them and the confidence level. So there you go. That's state. Step 2, plan. Okay, I'm going to abbreviate a little bit. I put the full details up above. I'm going to start with the word random. Is it random? Well, usually they tell you, right? So if you have a highlighter, you could highlight it, or if you're like in the middle of an AP test and you're not really supposed to use highlighters, you could circle it and say, look, it's random. I found the evidence. Yay. You can write yes given, and that's fine, but make sure that you actually check to see if it's given, because sometimes they'll try to fool you, possibly even in this homework that you're doing tonight. They might fool you by not telling you it's a random sample, and then you'd say, oh, it's not a random sample. Don't get to quit. You just have to say, sorry, it's not random, so I'm not sure that this is going to be right. Normal. Okay, how do we check normality? Let's look. We check normality by checking NP hat and NQ hat. So NP hat, Well, I'm going to go off to the side and say p hat is 57 out of 102, right? So important to know that. NP hat is the 102 times the 57 out of 102. And as you are super smart math people, you can look at that and say, oh, look, the 102s cancel. That's convenient. It's 57. That's what I meant when I said that the NP hat is actually the number of successes in your population. What's Q hat? Well, 102 minus 57, whatever that is, over 102, right? It's 45, by the way. So it's 45 over 102. So I'm doing a little bit of calculations off to the side to say, okay, had enough information, but it might be nice to know the fractions. So I could say NQ hat is 102 times the 45 over 102. I don't need the decimal. I could just say, look, it's the fraction, and it's a lot easier as a fraction because it cancels. These two numbers are beautifully bigger than 10. So I can look at that and say, okay, this one's met. Hurrah. I could even say yes over here if it makes me happy. Yes, because of these two things being bigger than 10. Independent. So now I don't know how many pennies are in my jar, but I'm pretty sure it's going to be over 1,000 pennies. It's a lot of pennies. I mean, 100 pennies is only $1. I know I have at least $10 in there and probably more. So I'm going to say yes. Since we're not quite sure, I'm going to assume that 102 is less than or equal to 10% of all my pennies that are in the jar. If I'm not sure, it's okay to assume. If the pennies are such a small amount that I can count them, then probably this wouldn't be met. But basically, I'm talking about the number, sample size, and I'm talking about what's my population. I am pickier about this than the AP readers are. I will tell you right now, when you do this, you may not write, yes, N is less than 10% of the population, because this does not prove to me that you thought about it. I want you to think about it enough to prove to me that you really did think about it. So that means you have to put the number and you have to put the population for me. And like I said, I'm picky about that because I've had so many students who just write N is less than 10% and they don't actually check. So I want you to actually prove that you thought about it. So that's one thing that I'm super picky about. I'm just telling you now. All right, step 3. We're going to do the calculations. Woohoo! We're going to go P hat plus or minus Z star times the standard error, which I'll replace that in just a minute. So I'm going to do P hat, which is 57 over 102, plus or minus. I need to calculate my Z star. I don't have this one memorized. So I'm going to come off to the side and say, okay, Z star is inverse norm. Here's a normal curve because sometimes that helps me. I need 99% now, which means I'd have an extra 1%, which is a 0.5% on this side and a 0.5% on that side. I need this piece right here, which is the half the extra thing. I need 99.5% written as a decimal. So that's the tricky part that I didn't warn you about, sorry. So let's go second vars, inverse norm, and 0.995 would give me the Z star critical value for 99%. And it should be bigger than 1.96, right? 2.576, round it off. So that's how I got that. And once again, I'm doing some extra calculations off to the side, but it doesn't hurt me any. Times my standard error. So here's where I'm going to put my P hat and Q hat. I didn't ever bother finding the decimals for those, but I could if I wanted to, or I could just write it as fractions. That doesn't bother me because the calculator can handle this. Over 102. The weird thing about writing it as fractions is the 102 really does appear 3 times in the formula if you write it in fraction form. If you write it in decimal form, it doesn't look quite so weird, but that's okay. If I divide this on my calculator, I get 0.559. And then I'm going to do this whole thing. Actually, I'm going to demonstrate good calculator form. 57 divided by 102, and then times the 45 out of 102. You could put parentheses if you wanted to. In fact, maybe I will. If you want to type this all at once, you can. Out of 102 times 45 out of 102 divided by the 102. Well, you can't really see that, but that's okay. That's the thing under the square root, and then don't forget to square root it. I got a 0.049 as my standard error. I'm going to multiply it by the 2.576 and get my margin of error, which is 0.1266. I'm going to leave 2 decimals on that, I think. And then I'm going to change this into an interval. So remember, I want my lower bound and my upper bound. Here's a tricky thing. Subtract first and then add. If you do it backwards, I'll get annoyed. Minus that margin of error that I just had. And this time I'm going to round it to 3 decimal places. So 0.432. And then if I go back to the margin of error and I do 0.559 plus that, then I get 0.686. If you put them backwards, I get annoyed because the interval notation is really supposed to have the lower number first and the upper number second. I know I'm picky. That's okay. This is the answer to the do stage right here. And last but not least, what does this mean? We are, how confident are we? We are 99% confident, because I did a really wide interval with this thing, that another way of saying it, rather than mentioning the word interval, you could say between 43.2% and 68.6% of all my pennies are, what about them, are over 10 years old. So again, we're using the numbers. We're saying how confident we are. We are saying what the population is and what the definition of success is. So those are important elements that you want to always include. And we're not saying that this is a probability or anything like that. It's not a probability. And we'll talk about that some more on another day when we haven't had such very long notes. I'm going to do one more thing, and that is interpreting. Sometimes you're asked to interpret the confidence level. And that is 99%. What does this 99% actually mean? It means that if I did this over and over again with lots of different samples, that 99% of those samples would capture it. So 99% of all random samples would produce an interval that captures the true proportion. And let's add some context of pennies that are over 10 years old. There. We will do a whole lot more of this next week, and you'll get really good at it. Promise. Practice makes perfect. Sorry about the long notes. We'll try to keep the next one shorter.